We're going to talk about more about probabilities today, as well as conditional probabilities and the multiplication rule. So first, what is a conditional probability? A conditional probability is the probability of an event occurring given that another event has already occurred. So the conditional probability of event B occurring given event A has already occurred is denoted by this notation here. So it's read as the probability of B given A. So we have the probability of B. This vertical line in math often means the word given. We use it with set notation as well. So the probability of B given A. So what you want to think here is that if this occurs first, then what is the of that happening next? Okay, so that's what the idea we're thinking of. If something occurs first, and we want to know what the probability is of the second event happening. So that's a conditional probability. One event comes after a first event. So let's look at some examples here. And you want to remember that really anytime we're dealing with probabilities, you're really thinking about that part over the total. And this is true for all types of probabilities. So whether we have the more classical example, like in this first case here, or whether we have the empirical example, you're still thinking part to total to get those probabilities or those proportions. So let's look at the first one. Two cards are selected in sequence, so meaning in order, one in a row, one before the other, from a standard deck of 52 playing cards. Find the probability that the second card is a queen given the first card is a king. And we're going to assume that the king, sorry to say king, is not replaced. Okay, so think about this. You have a deck of cards, right? You have 52 cards. And the first card that I pull is a king. And then the second card is the queen. So we're trying to figure out what is the probability of this. So what's the probability of pulling a queen after we've already pulled a king, right? And we're not replacing the king, so it's not like you're putting the card back in the deck. So maybe you're dealing cards or something like that. So you have the king in your hand, and now you want to know what's the chance of getting a queen next. Well, you still have that king as well. So think about your total and your part here, right? So your probability of pulling that queen, given we've already pulled the king. So I'm just going to use Q and K here for our events to make it a little bit easier to see. Well, how many chances are there of getting a queen? So if you think of a standard deck of cards, you have your four suits. You have, let's see, your hearts, your diamonds, your spades, and your clubs. Each of those has a queen. So there are 4 queens in the deck. And there are 52 cards altogether, but keep in mind you've already pulled a king. So there were 52 cards, but now there's only 51 cards left because you've already taken that king out. So our probability here is 4 over 51. And if we use our calculator, we get about 0.078, rounding to 3 decimal places. So these are our conditional probabilities. What's the chance of the second event happening given that the first event already happened? And what you're going to see is sometimes the first event affects things and sometimes it doesn't. It depends on the kind of events they are. So here, our first event affected things because instead of having 52 cards to choose from, we only had 51 cards to choose from. So we do have something being affected here. We have to be a little bit more careful. Let's look at the other example. So the table shows the results of a survey in which 2,276 social media users were asked whether they've ever been offended by something. It could have been a post, a comment, or photo they saw on social media. So basically the people answered, yes, I was offended, or no, I have never been offended. So we want to find the probability that a user is a male given that the user was offended by something on social media. So this word given is a really big flag that you have some sort of conditional probability. So you have one event occurring after another event has already happened. So obviously there are other ways to phrase things too, but that word given really comes in a lot when you see conditional probabilities. So we're looking for here is that we're finding the probability of a male. So probability of a male given that the user was offended by something on social media. So the user was offended, so they had said yes. So I'm just going to use M for male and Y for yes to make this easy to understand. Okay, so what happened here is that first, we're looking at only the group who says yes. Then within that group, we're looking for the part that is male. So given the user was offended by something. So we already know that we're in the group where the people said, yes, I am offended. So I don't actually need to look at this whole table. I'm starting with just people who were offended, right? Given the user was offended. So I'm not looking at everybody. I'm looking at just the people who were offended here. So that's the first piece. Now within that group, what's the chance of getting a male? Well, our part here would be the number of males. So I have 532 males in that group, and my total is 1151. So about 0.462 if we use our calculator and round there. Okay, so you just want to be really careful. Watch for those keywords. The phrasing with probabilities is particularly important. Words like and versus or versus given make a huge, huge difference. That word not. So if we're using complements, they're all very important. So you need to read these questions very, very carefully and see if there's an order there. So here there are orders given, right? Here we've pulled a card first, that's a king. So that's already done. And now we're thinking about the probability for the queen. Here, we're only looking at users who said yes to being offended, and now we're choosing the male participants after that. Okay, so we do have an order here. Now, this brings us to the idea of independent and dependent events. So in some experiments, one probability does not affect the probability of another event occurring. I don't know why I keep making that typo. Event occurring. For instance, when you roll a die and toss a coin, the outcome of the die does not affect the probability of the coin landing heads up. So these events are independent, right? So think about it. If I roll a die and I toss a coin, in no way is the die affecting the coin, right? They're two totally different things. So even though I'm doing the events one next to the other or side by side or one before the other or one after, it doesn't affect it, right? So for instance, another example, just kind of a fun example. If I wear my raincoat today, does that affect that it's going to rain outside? No, right? We have to be careful in the order here. But if I'm talking about, okay, I'm going to wear my raincoat, does that cause the rain to actually happen? No, it doesn't, right? So we have to be careful with events here. The other way around is different, right? If it's raining, does that affect if I wear a raincoat? Yes, it does. But me wearing a raincoat does not affect the rain. So we have to be careful how we're thinking about things when we talk about events here. So events that are completely independent have no relationship like that together. So the rain and the coat, although they have a relationship in one case and not the other, would not be totally independent events, right? If we think about the rain affecting what I wear, that would not be independent. Those are dependent on each other. So something that is totally independent means that one does not affect the other one in any way whatsoever. So two events that are independent occur when one event does not affect the probability of the other event. Okay, so the first event does not affect the other event. And we use, again, that conditional notation here is what's going to help us check this. So what it says is that depending on which way your event is going, the probability of event B given A is the same as the probability of B, or the probability of event A given B is the same as the probability of event A. So what this is saying is kind of tough to read, but what it's saying is that that given event here is not affecting the probability. So the probability of event B is the same whether I start with event A or I don't start with event A. Or the same thing here. The probability of event A is the same whether I start with event B or I don't. So it does not affect the other. Events that are not independent are dependent. Okay, so again, we have to be careful because sometimes the conditional one way could be fine, but not the other way, like the rain and the code example I gave you, right? So we just need to be really careful and think about our events and really what we're looking at for that particular problem. Now, to determine if events are totally independent or dependent, we can find the conditional probability and the other regular probability and see if they're the same. So we can use this idea here for independence. If the conditional and the regular probability are the same, then our events are independent. If they're not the same, then you have dependent events because that event A is affecting event B here. All right, let's do some examples. I think it'll make more sense. All right, so going back to some examples we looked at already. So selecting a king from a standard deck of 52 playing cards, not replacing it, and then selecting a queen from the deck. So we already looked at this example, but now we're going to kind of think of it from the idea of independence versus dependence. So we're letting A be selecting the king, and we're letting B be selecting the queen. So again, we're going in a specific order, which matters a lot in our examples. So we select the king first, then we're selecting the queen. So we're wondering, is there a connection there? Does one affect the other? So we're trying to figure out here the probability of B, given that A has already occurred. And then we're going to compare that with just the probability of B. Now remember here, I'm using B and A like in your book, but A was selecting the king and B refers to selecting the queen. Now we already saw from the previous example that that probability of B given A, just coming back here, was 4 out of 51, right? Because we said when we pull that king and we don't replace it, we're down one card. So it's 4 out of 51. If we look at just the probability of getting a queen without pulling the king first, so this one here is the probability of a queen without pulling a king first. Well, I have 4 queens in the deck, and then if I haven't pulled any cards yet, I would have 52 cards to choose from. So we can see these probabilities are not the same, right? These are not equal. So our events here are dependent. Okay. Now, I don't even think you have to even do the numbers here just to think about it. So if you think about playing with cards, if I pull a king from the deck first, that now changes my total. So it's going to change that fraction automatically when we're doing our calculation, right? If I'm pulling a king from the deck and then I'm choosing the queen afterwards, I've definitely affected the probability for that queen because I've changed the total number of cards that I can choose from. I went from 52 cards down to 51. So that clearly is affecting what's happening with that queen choice. So we have dependent events here. In the second case, we're looking at tossing a coin and getting a head, and then rolling a 6-sided die and getting a 6 on it. So again, I'm looking at comparing probability of B given A and the probability of B. So the probability of, first of all, let's do B first. The probability of just getting a 6 on a 6-sided die, well, my options there are 1, 2, 3, 4, 5, or 6. So to get a 6, I have a 1 out of 6 chance, right? There's one number 6 and there's 6 numbers all together. So the chance of getting a 6 is 1/6. Now, what's the chance of getting a 6 after I get a heads on the coin? Well, think about this. Is me flipping a coin going to affect how the die rolls in any sort of way? And again, you're assuming that you're not going to like have them hit on the table or bump into each other, right? So we're doing these, flip the coin first, that's done, now roll the die. So they shouldn't be affecting one another. So this probability here is also 1/6. You still have a 1 out of 6 chance of getting that number 6 on the die. So these are the same. So you have independent events here. So to find independent or dependent, you can do out the calculations if you want to. So if that's helpful for you, or if you're unsure, definitely do those calculations out. But a lot of times we can just think about it and just say, okay, does that affect the other thing? And in this case, pulling a card from the deck first and then pulling a second card, yeah, there's change there because we have that king already out of the deck. So I've changed my total from 52 to 51. In the second case, a coin and a die have really nothing in common. They shouldn't affect each other, so you have independent events there. And for the last one, driving over 85 miles per hour and then getting in a car accident. Now, for this one here, again, we're looking at the probability of getting in a car accident, given that we're driving over 85 miles per hour. I don't have numbers here, so I can't actually find the numbers, but just think about this, like use your common sense. If we're driving faster than 85 miles per hour, would that affect us getting in a car accident, right? So what this says here is the probability of a car accident given you're driving greater than 85 miles per hour. So sometimes it helps just to use words instead of A's and B's. You can write that right in. So B is getting a car accident, A is driving fast. So what's the probability of a car accident given that we're driving very fast? Is it going to be affected? It's absolutely going to be affected, right? If you're driving that fast over 85 miles per hour, you definitely have a higher chance of getting in a car accident, right? You have less control of that vehicle if something were to happen. So these are dependent events. And again, I know that not with looking at the numbers, but really just using my common sense that speed can affect a car accident.